There is a caveat here that the subtractions have to be performed algorithmically or iteratively, perturbatively, which means that when you go to two loops, you have to have already performed the subtractions to one loop and so on and so forth. It's kind of easy to describe. For example, you can have these two loop diagram, and you can check that the number of internal momenta, when you impose all conservations of momentum at the vertices, the number of independent momenta besides the external momenta, which you call internal momenta, is the number of loops. Actually, that's the definition of the number of loops. The number of loops is not what you can visualize as a loop. The number of loops, because in more complicated diagrams, can be very difficult to count so-called loops. The number of loops is the number of independent diagram loop momenta on which you have to integrate. And when we made this kind of argument here, we just took care of one divergence, the divergence that arises when all of the loop momenta go to infinity. So when you differentiate your integral a certain number of times, it becomes, it's said, overall divergent, which means that when all the internal momenta k squared go to infinity, it will be divergent. But still there is the problem of the divergence, subdivergences, so-called, when some only of them go to infinity. However, that's already taken care of perturbatively, because in this case, for example, you see this is a subdiagram, but that's precisely the diagram we have already considered. That's one internal momentum only, k, and if you have subtracted a vertex, some constant that subtract this one, this b lambda squared log lambda. You see, it has the same form of I lambda, so you can subtract that by adding a vertex or redefining lambda. You can redefine lambda as lambda nu plus delta lambda, and the plus delta lambda is is this. So you can do it the way you like. The point is that when you have taken care of that at two loops, you will find that you won't have just that, but you will have also something like that. So you will discover that all subdivergences will be automatically taken care of, and only the overall divergence will remain. And this argument tells you that the overall divergence is local, and then you subtract the overall divergence in the same way, and you go on. However, so that means that you can subtract the divergent parts, which are polynomial, by correcting your Lagrangian. Because in the Lagrangian, every term of the Lagrangian should contain a finite number of derivatives. And the theorem of locality of counterterms tells you that every counterterm has the same property. It is local in momenta, so it contains a finite number of derivatives and a certain number of fields. How many fields? For example, 4 here. If you compute a diagram with 6 legs, then they will be 6, and so on. So every time you have a divergent part, you know how many derivatives you have there, because the polynomial, the divergent part is a polynomial, and how many fields and how they are distributed, because the momenta are different for different external legs. So you basically subtract them by means of correcting your Lagrangian. Now the point is, either your starting Lagrangian contains already all the types of terms that you generate by means of diagrams as the divergent parts, and so you just have to modify the starting Lagrangian by means of constants in front of the terms. That theory is called renormalizable, or not, in which case you have to add new terms that were not present in the Lagrangian. If the number of terms you add is finite and the procedure closes after a finite number of additions, types of terms, then the theory is still renormalizable. If not, the theory is not renormalizable. So for example, the phi to the fourth theory is renormalizable. Let's say the counter terms are local, like the terms of the Lagrangian. And can be subtracted by modifying the Lagrangian. Point is that we can perform a number of unobservable operations only if we redefine the ingredients of the Lagrangian we started with, the coupling constants and the fields. But if we add a totally new term that was not there, that's not a redefinition. It's not an unobservable thing. So the starting Lagrangian may or may not contain all the types of local terms it generates as counterterms by means of Feynman diagrams. If yes, the theory is renormalizable. If not, new terms must be added to the Lagrangian. If a finite number of additions is sufficient, the resulting theory now, not the initial theory, is renormalizable. If not, the theory is non-renormalizable. So before going to gravity, we see two cases with scalars of theories. One is renormalizable, that's phi to the fourth, and it is basically like the standard model. And the other one is not renormalizable, like gravity, and that's phi to the sixth. Sufficient to change the power in the potential, and you get for example, why is the phi to the sixth theory renormalizable? Let's consider its Lagrange. Well, here you have Feynman rules, which are similar to the ones we had before. But now you have a vertex with 6 legs. Like that. Let's consider a very simple diagram built like this. These are two vertices with 6 legs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But this integral you get is exactly the same integral we got before, because the internal part is exactly the same. The internal part here is exactly the same. Whatever the number of legs you may add, they are external, and the diagram is amputated, so they don't change anything. We know already what the divergent part of this integral is, so if you want to compute the divergent part of that, it will be a constant, a logarithm, independent on the momenta. That's fine, it's local, times a certain number, c. But the point is that you cannot subtract this. This is local, fine. But this is a counter term, a local counter term with 8 external legs, because you have 1, 2, 3, 4, 1, 2, 3, 4. So to subtract it, you must add some delta here, phi to the 8 factorial, and so you will get here minus I delta. And if you adjust your delta, the sum of these two, which will be when you will meet this when you compute the 8-point function. So if you correct your Lagrangian, you will have that. That will be convergent, yes, when lambda goes to infinity. But the point is that to reach that, you have to change your Lagrangian by creating a new interaction. It's not sufficient to redefine the constants of the fields. And after you change by adding phi to the 8, you will have a vertex with 8 legs, and you will be able to build a diagram, same diagram, with 10 external legs, and that will force you to add phi to the 10 with the same divergence, and from phi to the 10 to phi to the 12, and from phi to the 12 to phi to the 14, and you go on. And the Lagrangian will contain infinitely many terms. And then those infinitely many terms for R should be multiplied by arbitrary coefficients here, new coupling constants, because there is no reason, it can be shown that there is no privileged choice when it comes to determining those coefficients. There is no way to determine them, so the theory sort of becomes completely arbitrary. That is a non-renormalizable theory. Instead, the phi to the 4th theory can be renormalized and its renormalized version can be written as the starting one by means of a number of constants, which are called renormalization constants. 3 terms we have, so you use 3 constants. The first constant is z phi, the second constant is z phi times zm squared, because it's the mass term. And the third constant is written as z lambda z phi squared phi to the 4th. Important thing is to have 3 independent constants, because so all the divergences of these diagrams in phi to the 4th can be of this can only be of this type. For example, you can check that there is no divergence with phi to the 6th in phi to the 4th theory, because this diagram, for example, a diagram like this has 3 propagators inside, so you will have an integral on a loop momentum, but you will have 3 propagators, and that's convergent for k squared much larger than lambda squared. So when you complicate the diagram, it will become more convergent, at least here. Well, it turns out there is a very simple rule to have control on all this, which is called power counting. And that means that you check your starting Lagrangian and start giving dimensions to the various ingredients in units of mass. So for example, in 4 dimensions, the Lagrangian should have dimension 4, because the action, which is the integral d4x of the Lagrangian, is an action, so you know the action has dimension 0. It's an h bar. And h bar can be set equal to 1. But if the action has dimension 4, and of course the mass has dimension 1 in units of mass, then this should have dimension 4. So that means that phi has dimension 1. And the derivative, of course, is like a mass. It's an energy, so it has dimension 1. But if this has dimension 4, lambda phi to the 4th, that means that lambda has dimension 0. Now you understand why there cannot be any counter term that can be generated, this one, with many phi's or many derivatives, because we have written all the terms with dimension 4 with no dimension. You see, we do not have parameters with negative dimension. So you cannot even write a candidate counter term for lambda to phi to the 6, because phi to the 6 has dimension 6, and you would have to multiply it by a lambda 6 that has dimension -2. But since we have proved that the counter terms are local in phi in derivatives, they cannot contain derivatives to the denominator, they cannot contain masses to the denominator. This we have to spend a minute on that. You cannot even build a lambda 6. Yes, one thing that we didn't say, but it's obvious, it's another consequence, is that not only the counter terms are local, they are also polynomial in the masses. The story is the same. Instead of differentiating with respect to P, differentiate with respect to a mass. And you will obtain something that's much more convergent because the masses are in the denominator. So if you differentiate instead of the external momentum, instead of differentiating with respect to external momentum, you differentiate with respect to the masses. Since they enter the propagator, everything will become more convergent, and so after a certain number of derivatives with respect to the masses, you will get 0. Bottom line is that you cannot even construct those counter terms because they have to be local, they have to be to contain the parameters, all parameters polynomially, the couplings because they come multiplying in vertices, so the couplings are polynomial, the masses are polynomial, the phi's, the number of external legs, phi, 6, whatever they are positive powers, you can have 1 over phi. You cannot have 1 over derivative because it's local, so you cannot even build this. On the other hand, if you start from a phi to the 6th theory, you can so again, phi has dimension 1, but this implies that lambda 6 has dimension -2. And when you have something of dimension -2, you can build phi to the 8, because this has dimension 4. And you can build phi to the 10, because this has dimension 4. And you can build phi to the 8 box, phi to the 8, with the sufficient number of lambda to the 6th in front. And the general rule is that everything in renormalization that can go wrong will go wrong. And so every kind of counter term you can build will be generated by some diagram at some level, at some order. Only miracles or symmetries, but powerful symmetries have never been found. Powerful enough symmetries have never been found. They can kill some counter term here and there. There is no symmetry that's sufficiently powerful to beat the power counting. Now, phi to the 6 is similar to gravity, phi to the 4 is similar to the standard model. So this is the difference between gravity and the standard model. The theory of gravity will be is, at least if you start from the Hilbert action, non-renormalizable. And so we can start moving to gravity, finally. We have seen that the action is something like this. This is the gauge fixed action, and there is the ghost part. The ghost vertices are simple, so let's focus on the Hilbert part. And this we can expand around flat space. Plus 2k phi mu nu. Phi mu nu is the fluctuation. So we have seen that this object, when we expand the quadratic part, we have worked out. How was the quadratic part? We recall that in the quadratic part, this k squared disappeared because there are two k phi. 2k phi simplify the k squared. And so you remember that we had two phi's with two derivatives. Two phi's and two derivatives. This is the quadratic part. So this was the quadratic part. A sum of terms like that, no constant in front, but since the integrand must have dimension 4 and the derivative has dimension 1, this phi also has dimension 1. But this is bad, because if this has dimension 1, since the metric has dimension 0, because eta has dimension 0, that means that k has dimension -1. The coupling constant of gravity, kappa, has dimension -1. And that is why you can build infinitely many counterterms, and you will find them in loop diagrams. Well, if you work out the vertices here, for example, the cubic correction in the expansion around flat space, what will you obtain? You will obtain 3 phi's, because it's cubic, and then there will be corrections. So we are expanding around flat space, right? So it's a Taylor expansion. There is no linear term. The linear term is a total derivative. That's why it disappears. But there is a quadratic term, then will be a cubic term, a fourth order term, so on and so forth. How many derivatives are there here? The number of derivatives is always 2, because R is that. So the number of derivatives is always 2. There is nothing that can raise or lower the number of derivatives. There will be two derivatives here and there. And what is the power of kappa? There is a kappa for every phi. So if there are 3 phi's, there is 3 kappas. There are 3 kappas. Divide -2, so there is 1. And then you can continue. All other terms will be, each of all other terms will have 1 more kappa and 1 more phi. Same number of derivatives. So you see it's different from the phi to the 4th theory. If you want, you can go on. So with 4 phi, you can have something like this. There are not just 4 phi's like in phi to the 4th theory. There are 2 derivatives. And those 2 derivatives raise the degree of divergence of every diagram, because you will not have a constant vertex like you had in phi to the 4th. This thing will be the polynomial in momenta. The polynomial with momenta will affect the integral because it will give numerators in the integral, in the integrand, and that will raise the degree of divergence, so on and so forth. So it's not like the phi to the 4th, it contains vertices with derivatives. From a point of view of renormalization, it's always the same. The point is that now you can construct many terms that are candidate counterterms and have dimension 4. For example, r squared. What is the dimension of r? Dimension of r, well, is the dimension of d gamma or gamma gamma. What is the dimension of gamma? Gamma is g to the -1 dg, basically. G is the metric, so it's 1 because there is one derivative. G has no dimension. So r has dimension 2 because it has 2 derivatives. So r squared has dimension 4 by itself. This is a candidate counterterm. I don't need anything particular to build this counterterm. So this has dimension 4. Then I can build all the quadratic terms we studied. And those are the first that appear, indeed. Well, there are only 2, we remember. The other 2 can be eliminated by means of Euler characteristics. So Weil squared is not independent, so on and so forth. But then you can build also this one, for example. Because this has dimension 6. I want something of dimension 4. I just multiply by kappa squared, because kappa has dimension -1. And then there are many, many terms that I can build of dimension 6. So, for example, r cubed. And then I can go to r to the 4th, which I multiply by kappa to the 4th. Infinitely many terms, and they are all turned on by renormalization and by one-loop diagrams because they have a different divergent structure. They have numerators brought by derivatives that occur in the vertices. 2 derivatives are enough. So this is the theory of quantum gravity and its problem with non-renormalizability. there are some simplifications we can make to drop many of those counter terms, but infinitely many will survive. Infinitely many independent terms. So if we want to quantize gravity this way, we will end up with an action that contains, it's not, so the Hilbert action is not renormalizable, it's meaningless from the point of view of quantum field theory. We will have to supplement it with infinitely many terms. However, at low energies, all these terms are negligible because this kappa is 1 as dimension -1, and indeed it is 1 divided by the Planck mass. Which is 10 to the 19 GeV. So those terms that you can build are suppressed by higher and higher powers of the Planck mass, which means that they become relevant when your R is considered, your curvature basically, is considerably different from 0, which may happen, I don't know, in the Big Bang in the very first times, or in black holes, or in certainly not in high energy experiments that you can make in laboratories, because we are very far from 10 to the 19 GeV at CERN. We are around TeV, 10 to the 3 GeV. So there is no chance to probe those corrections. So the theory is not renormalizable, but for all purposes, at low energies, this theory, even if it contains infinitely many terms, is okay because the corrections will never matter. And from the point of view of experiments, they might not matter for billions of years. So you can ask, why do we care about quantum gravity? No, I don't have an answer to that. But there are some things that we can do and say, and eventually they will lead to a solution. So if there is a solution, why not? To start this, we can see some properties that we have when we study those corrections and try, for example, to organize this action. Okay, this action has infinitely many terms, fine. That doesn't mean we cannot say anything about its properties or its predictions. At low energies, for example, those infinitely many terms don't matter at all. So the theory is predictive at low energies. Is it possible to say some other things? And yes, it's possible. Maybe we have time to conclude today with a way to organize those counterterms, proving a little theorem. Let's consider a diagram, an arbitrary diagram. And the question is, how many kappas do we have? There. How many constants kappa? Well, here we see that the generic vertex has kappa to the number, two derivatives. Let me write it symbolically like this, two derivatives, a certain number of external legs, n, and a number of kappa that is n minus 2. Because each phi has a kappa and there is a 2 in front. So let's consider a generic diagram and call L the number of loops, I the number of internal legs, and V the number of vertices. Then there is an identity which we already met actually, which is the Euler theorem for the polygons, that tells us that L is equal to I minus V plus 1. Which you can also write as L minus I plus V equal to 1 plus L minus I plus V equal to. It's like saying that in a polyhedron, the number of faces, remember the Betti numbers, minus the number of edges, plus the number of vertices is equal to 2, which is the Euler characteristics of the sphere. So here in the tetrahedron, the number of faces is 4, the number of edges 1, 2, 3, 4, 1, 2, 3, 6, and the number of vertices is 4. Here, check this diagram. L is 1, so L plus 1 is 2. So basically, there is one face here and the complementary face, the rest of the plane, two faces, minus I, the number of internal legs, that's 2, plus the number of vertices, that's 2. So L plus 1, yes. So L plus 1 is 2 minus 2 plus 2 is equal to 2. L plus 1 is 3, 2 loops, 1, 2, plus the complementary phase, minus the number of edges, 1, internal legs, 1, 2, 3, 4, plus number of vertices, 3, 2. That's always true. And thanks to this identity and very simple considerations, we may have a control on the structure of the counter terms. And I can tell you which counter terms will appear at which order of the expansion. And the order of the expansion is identified with the number of loops of the diagram. The number of loops is equal to the number, we will see it from the same argument next time, that the number of loops is equal to the power of h bar in front of your contribution. So it's what guides your expansion.